So far, we talked about different variants of SAT. In particular, we also talked about um, variants of SAT with alternating quantifiers, so defined polynomial time hierarchy. Very important related notion of SAT is counting satisfying assignments, and that's what we're going to talk about next. The problem is called sharp SAT, and it's defined as follows. You're given an input formula, maybe 3CNF, maybe a circuit, phi on n variables, and you want to output the actual number of all satisfying assignments for the formula phi, which can be expressed as this exponential summation where you try all possible Boolean assignments and evaluate formula phi on each and count 1 for each satisfying assignment and 0 for unsatisfying one. Obviously, sharp SAT is more difficult than SAT. And in particular, it's not hard to see, it's a triviality that NP is contained in P to the sharp SAT. If you can count, then you can decide if the formula is satisfiable or not. What is much more surprising is that if you allow yourself Oracle access to sharp SAT, not only can you solve NP, but you can solve any problem in polynomial time hierarchy as well. So you can eliminate alternating quantifiers, existential universal, if you have access to algorithm for counting satisfying assignments. And that's a famous result due to Toda from around 91, where he showed that polynomial time hierarchy is contained in P to the sharp SAT. Not a very interesting corollary of this result is that if I have a fairly good algorithm for sharp SAT, if we can count satisfying assignments in some sub-exponential time, like 2 to the n to the epsilon for some tiny epsilon, then by Toda's result here, we can put polynomial time hierarchy, every problem in the polynomial time hierarchy, also in sub-exponential time, because everything in polynomial time hierarchy is polynomial time reducible to sharp SAT. Polynomial time reduction can blow up the input sides only polynomially, and this polynomial blow-up is going to be eaten by sub-exponential time to the n to the little o1 time. So, of course, it's unlikely, and we'll talk about that more a bit later, that SAT, or even less likely, sharp SAT has a sub-exponential time algorithm, but it's still conceptually very interesting that before, in our early proof, where we showed that if you have a polynomial time algorithm, then you can collapse polynomial time hierarchy to polynomial time, that proof, if you think about it, does not show a generalized version where instead of assuming that SAT is in polynomial time, you assume that SAT is in sub-exponential time, and you want to conclude that, say, polynomial time hierarchy is in sub-exponential time. Even for sigma 2, we cannot improve and get sub-exponential time algorithm for a sigma 2 problem, because if you remember, you have this composition of the runtimes of your SAT algorithm. And if the runtime of the SAT algorithm was polynomial, then polynomial composed with a polynomial is still polynomial, so it's still good. That's how you get this result here. But if your runtime of the SAT algorithm is sub-exponential, composing sub-exponential with sub-exponential does not give you anything nice. Okay, so Toda's result does give you something nice, but you need to strengthen your assumption from SAT being in polynomial time to sharp SAT being non-trivial, like sub-exponential time or better. Another interesting thing is that you only need black box access to this sharp SAT algorithm, as opposed to our earlier proof collapsing the polynomial time hierarchy under the assumption of SAT as in P, where we needed white box. We needed a source code for the SAT algorithm to carry out that proof argument. So I'm not going to prove to you this fantastic result due to Toda, but I will talk about an ingredient in this proof, which is interesting in its own right, because it talks about another very important problem of variant of satisfiability, so-called unique SAT. So unique SAT is a problem to distinguish between formulas which are unsatisfiable and formulas which have exactly one satisfying assignment. So your input is promised to be of two kinds, either the number of satisfying assignments is 1 or the number of satisfying assignments is 0, and you want to tell which. Obviously, unique SAT is reducible to SAT. If I have a SAT algorithm, then I can answer unique SAT questions easily. If formula is uniquely satisfiable and predictably satisfiable, if it's not satisfiable, then it's still not satisfiable. So the reduction here is very trivial, just the identity function. What is much more interesting is kind of the other direction, where if you know how to solve unique SAT, then you can solve general SAT as well. And that's somewhat surprising. It was surprising at the time when this result was proved by Valentine and Vazirani. Basically, they've shown that satisfiability is probabilistically polynomial time reducible to the problem of unique SAT. So here RP stands for randomized polynomial time. Basically, it's a Turing machine which is allowed to flip random coins. And unlike the deterministic machine, it will now have some probability of getting the correct answer and some probability of making a mistake. And it's an RP machine if its probability of making a mistake is relatively small, is bounded by, say, less than 10%. So let me explain to you how does SAT reduce to unique SAT in a randomized way. That's this famous result due to Valentine and Vazirani from around 1986. And the way I will state this result is a randomized transformation that will take an input formula phi, again, maybe phi is a 3CNF, and will output a list of new formulas, psi1, psi-n, all of them on the same set of n variables as phi. But if phi was a 3CNF, psi1, psi-n will no longer be 3CNFs necessarily. You'll see why in a moment. But the property of this randomized transformation, mapping a single formula phi to this small list of n formulas psi sub 1 to psi sub n, is the following. If the original formula phi was not satisfiable, then each of the produced formulas psi sub I will not be satisfiable as well. On the other hand, if the formula phi was satisfiable, then with some non-trivial constant probability, say at least 1/8, this randomized procedure will produce a list such that at least one formula on that list, at least some sub I, will be uniquely satisfiable. It will have exactly one satisfying assignment. So it's not hard to see that if I have such a randomized polynomial time algorithm, and I do have it, it transforms formulas to list of formulas. Then if you give me an algorithm for solving unique SAT, using this transformation and that algorithm for unique SAT, I can also solve SAT. How? Give me an instance of SAT. I will perform my reduction given by this procedure. I will compute the list of formulas using randomness. And then I will run my unique SAT algorithm on each one of the formulas in the list. If on at least one of them it answers yes, then I will say accept, formula phi is satisfiable. And if my unique SAT algorithm will answer no on all of the formulas, then I will say no, my original formula phi is not satisfiable. And you should see the correctness of this algorithm that I describe. It's immediate from the definition of the reduction in Valentine and Vazirani's procedure. If the formula is satisfiable, all formulas psi sub I will be unsatisfiable, so unique SAT algorithm must answer no, 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 no for each one of them. On the other hand, if the formula phi was satisfiable, then with decent probability, at least one of the formulas on the list will satisfy the unique SAT promise that it has exactly one satisfying assignment, so the unique SAT algorithm must answer yes. And so I will get the answer yes in this case, with probability at least 1/8. And it's the usual thing. You can boost the probability of success by doing some repetitions and taking majorities and so forth. Okay, so you'll get a randomized algorithm for SAT if unique SAT is in probabilistic or deterministic polynomial time, for example. So in this sense, unique SAT is like very difficult. It's as hard as general SAT. If you can solve unique SAT efficiently, then you can also solve general SAT efficiently. but now you have to use randomness. And it's open problem whether you can de-randomize this construction and reduce the amount of randomness needed. It seems to be very difficult to do so. Okay, but let's get back to the reduction in Valent-Vazirani's result. So I want to give you a proof idea of how you built this list of formulas, psi sub 1 to psi sub n, from a given formula phi that you start with. So what you're going to do is use randomness by creating a random XOR constraint as follows. You pick at random a subset of indices between 1 and n, set capital S, and you pick a random bit b from 0, 1, and then you define the following XOR constraint, h sub s comma b on x1 through xn, to be saying that if you look at the parity of the bits xi indexed by the set s, then their parity is equal to b. Okay, so it's a random parity constraint on the set of variables x1 through xn. So how does it help to introduce this random parity constraints? Well, let's think. Suppose I have formula phi on n variables, which has some number capital M satisfying assignments. Let's assume that M is positive, so formula phi is actually satisfiable. Then if I take a random constraint h sub s comma b and put the conjunction of phi and this constraint, getting a new formula, the number of satisfying assignments in this new formula, phi conjuncted with h sub s comma b, intuitively will reduce by a factor of 2. Why? Because a random parity constraint is likely to kill off, or expected to kill off for sure, half of the assignments in the formula phi. So if you look at any assignment that was satisfying formula phi, that assignment will satisfy a random parity constraint h of x1 through xn with probability exactly 1/2. Okay, that's not very difficult to see thinking about random parities. So we expect to halve the number of satisfying assignments in the formula phi after conjuncting phi with one random constraint. Now, if you repeat it a few times, then you reduce by a factor of 2 in expectation each time. And so intuitively, if you do this random parity constraint addition about log of capital M times, where M, remember, was the number of satisfying assignments, and put phi conjuncted with this bunch of random parity constraints, then you expect to reduce the number of satisfying assignments of phi to 1. Okay. Of course, all of this is in expectation, and we want to produce a random formulas psi sub 1, psi sub t, such that with non-trivial, relatively high probability, like 1/8, one of them is uniquely satisfiable if phi is satisfiable. So how do we go from expectation to something that happens with reasonably high probability? Well, this reduction from expectation to the high probability follows from the properties of this random parity constraints. The property being two-wise independence. And if you've seen hash functions before, then you would recognize that basically these h's are random hash functions whose range is 1 bit. And if you take k of them, then you'll have a universal hash function whose range is k bits. And then you just need to figure out what the right range k is so that you isolate exactly one satisfying assignment of the formula phi. That seems to be a big problem, right? Because we don't know what is the number of satisfying assignment of a formula phi. So we don't know how many this random XOR constraints to take. However, it's enough to get an approximate value, k, such that the actual number of satisfying assignments for the formula phi is between 2 to the k minus 2 and 2 to the k minus 1. So if I know the sharp sat of phi to within a factor of 2, roughly speaking, then that's enough. Why is it good? Well, there are only n possible factors of 2 to approximate the number of satisfying assignments for phi, because the number of satisfying assignments of phi is some number between 0 and 2 to the n. So the number of powers of 2 is like 2 to the 0, 2 to the 1, 2 to the 2, and so forth, 2 to the n. So there are only like about n possibilities for my power k here. And I don't know which k to use, but there are not so many of them, so I will try them all. Okay, and that's how I get the list. So I try each value of k between 2 and n plus 1, say, and I will form using randomness and do it independently for different psi's. I form psi sub k by taking my original phi and picking k independent random parity constraints, these hash functions I mentioned independently, each one, and put the new formula phi and conjunction of this parity constraints. And I do it for k's ranging from 2 to the n plus 1, so I get a list of n formulas in the end. Okay, and I will not be given the computation here. It's some simple calculations based on the pairwise independence that allows you to argue that this process succeeds with probability at least 1 over 8, meaning that if I built a list of this psi sub k formulas like I described, then if formula phi was satisfiable, then with probability at least 1 over 8 for the correct choice of k, which gives me the right approximation here, I will get unique satisfying assignment isolated by restricting with this k random parity constraints. Okay. So as I mentioned, this result was part of Toda's proof, but it's also a very exciting result on its own. It allows you to basically focus on the hardest case of satisfiability, which is unique satisfiability. So you can assume when you design your SAT algorithm that your formula, say without loss of generality, is uniquely satisfiable, and try to analyze your SAT algorithm for that special case. And by the Valentine reduction is as general as needs to be. Great, so what else can we say about sharp SAT? Well, sharp SAT is a very interesting problem. On the one hand, it's very hard, as we saw. On the other hand, it does have some kind of notion of efficient provability associated with it. So sharp SAT can be shown to have so-called interactive proofs. So let me talk about interactive proofs for a moment. As you remember, when we defined the notion of class NP, I used this prover-verifier interaction, the game between the prover-verifier, where both of them were given input X, and then the prover would send a proof or a witness to the verifier, and the verifier will check if the proof is valid given the input X. Now, we're going to generalize this definition, this game between the prover and verifier, to allow two things. One, we allow multiple rounds. So prover and verifier will talk for some polynomial in n number of rounds by exchanging messages. The messages that the prover sends and also the verifier sends will have to be polynomially bounded, because the verifier is going to be some polynomial time algorithm. It cannot possibly look at very long messages given its restriction on the runtime. So the prover has to send short messages to the verifier, same as was the case for the standard classical definition of NP that we saw earlier. The verifier, in addition to interaction, the verifier is also allowed to be randomized now. And here in this picture is captured by saying, okay, the verifier will be sending to prover some random bit strings each round. So the challenges that the verifier sends to the prover are encoded in random strings Z1, Z2, and so forth. So you have an exchange. Prover sends some Y1. The verifier challenges by sending random bit string Z1. The prover replies by sending some message Y2. The verifier challenges again. And after polynomial many rounds, verifier looks at the whole transcript of the computation on all the messages being exchanged and must make a decision to accept or reject. And the way we define the verifier's decision, it will be some polynomial time algorithm, capital V, such that you apply this polynomial time algorithm to the input X, and all the messages exchanged, y1, z1, y2, z2, and so forth. Note that even though V is a deterministic algorithm, because the verifier is using randomness, random messages, z1, z2, and so forth, this algorithm V is actually a randomized polynomial time algorithm if we think of randomness coming from verifier's choices of the messages z1, zt. So we have interaction and randomization, and with these two ingredients, we have a proof system which is seemingly more powerful than the classical proof system for NP, where we had only one round and the verifier was deterministic polynomial time algorithm, no randomness used. So what does it mean to for a language to be in IP, in the class IP? We can define the class IP and say that a language L is in the class IP if there exists a polynomial time verifier V such that for every input X, if X is in the language, then there exists a prover that is able to convince the verifier to accept with probability 1, where the probability over the random strings chosen by the verifier, those Zs that I mentioned. And this is called completeness. So if X is in L, then the verifier can be made accept, can be convinced to accept with probability 1. Soundness says that if X is not in the language, then no matter how clever or how devious the prover is, the verifier will accept with probability bounded away from 1. The probability over randomness Z1, Zt that the verifier accepts is going to be, say, less than 1/3. So you have a gap between completeness and soundness, 1 in one case and at most 1/3 in the other case. So what I want to do next is give you an algorithm or an IP protocol for solving sharp-SAT. One small difficulty is that sharp-SAT is not a language, it's not a decision problem, but it's very easy to fix using standard tricks. So let's define the decision version of sharp-SAT, denoted sharp-SAT sub D, as follows. As input, you're given two things, a 3CNF formula, phi, on variables x1 through xn, and the parameter k, the number between, an integer number between 0 and 2 to the n, which supposedly is the number of satisfying assignments of the formula phi. And you need to decide if it is indeed the case that phi has k satisfying assignments. What we will show next is the following beautiful result of Lund, Fortno, Karlov, and Nissan from around 1990, that this problem sharp-SAT decision version has interactive proofs. And we'll do that in a moment.